All right, hey guys, so today we're going to go over nonlinear inequalities and regression. As a recap, an inequality is just a relation of two algebraic expressions where one of the expressions is greater or less than or greater than and equal to or less than or equal to another algebraic expression, right? For example, we have x greater than 5 for x plus 5 is less than 20, x plus 5 is greater than 1. And the solution of an inequality is just a set of all values which satisfy the inequality. So, it's not a single value, it's going to be an interval, or, what we call a solution set. So, here's a step-by-step procedure for finding the solution set to a non-linear inequality. And the steps are similar to what you would do for a linear inequality. So first, when we get an expression like this, we want to move all the terms to one side of the inequality, as seen below. So you can choose whichever side you want. For now, I just moved it to the left-hand side. Then you want to solve for the zeros of the resulting expression. So, if it's a little too complex, you can use a graphing calculator to estimate the values of x for which, this is 0. So, I pulled out my graphing calculator and the values and the zeros of this equation are 0 and I think approximately 0.689. So, we can graph the expression by sketching, by hand, or, we can, find where the sign changes. But right now in this video, we're going to stick to graphing out expressions, mainly because I think it's a much more powerful skill set. So yeah. So I pulled out Desmos and I graphed out, the resulting expression when I moved all the terms over to the left-hand side. And the zeros are at 0, 0, and 0.689, comma 0. I'm sorry, that's a typo. So, we found the values of x for which this, expression is equal to 0. But we're mainly concerned about the values of x for which this expression is less than or equal to 0. So, looking at the graph, we know that, x goes as x is less than or equal to 0, for all values of x less than or equal to 0, this expression is less than or equal to 0. Same thing with the right-hand side. When we go beyond, or when x is greater than or equal to 0.689, this expression is also true. So now we found the intervals, which are negative infinity comma 0 and 0.689 comma infinity. And these two are our solution sets. Or actually, this is one solution set since we use the union operator. And this is the answer to our question. Just just as a refresher, the parenthesis is for an open interval and a square bracket is for a closed interval. So, in this interval, 0 also counts, and in this interval, 0.689 counts. And the union thing also just means, this set and this set both satisfy this condition. All right, so now we're going to move on to graphing. So, whenever we have a problem that asks, that gives one or more, two or more inequalities and asks, to find the intersection points and the shaded region that satisfies both inequalities, we want to follow this procedure. And we first do that by finding the intersection points by solving the system of nonlinear equations, basically finding where the two graphs intersect. So let's treat this as one equation, this as another equation. Let's not care about the inequality signs for now. Let's just act as if this is an equal sign and this is an equal sign and find where they intersect. Then we can graph them, right? So we can write this inequality as an expression in terms of x. So y is greater than or equal to x squared. We can move y to the right hand side. Same thing with this, we can move 2x squared to the right hand side. So we'll get y is less than or equal to 12 minus 2x squared. So we can graph those two equations and find the shaded regions of each inequality. So let's, essentially, this is what I did right now. I treated these two as equations and non-inequalities, found where they intersected, found the corresponding x and y coordinates, found the x coordinates and their corresponding y coordinate, and I graphed them out. All right. And yeah, I shaded the region that satisfies the inequality. And these two shaded regions are both form this sort of an ellipse, I think, right over here. Basically the figure I'm trying to sketch right over here. And that's the common region where a common region that contains points that satisfy both this inequality and this inequality. All right, let's move on. Here's some practice problems. So, before I reveal the solutions, I highly encourage you to try this on your own, right? So, feel free to pause the video and try this on your own. So, the first question is, solve for the intervals where the inequality x squared minus 5x minus 6 is greater than or equal to 0 is true. So, we first want to, solve for the zeros. So we factor it out, and we get positive 6 and negative 1. Now we can graph this function by hand. It's not that hard. We see that for all values of x in the open interval, negative 1, 6, the inequality does not hold. So this inequality holds true for all values of x in the interval negative infinity, negative 1 in the closed interval, and closed interval of 6 and positive infinity. So basically we're saying this inequality is true for all values of x that are less than or equal to negative 1, and all values of x that are greater than or equal to 6. Problem 2. So we're given this inequality, so we do the same step as always. We move the term on the right hand side to the left hand side. Then we want to solve for the zeros of this expression, which are negative 2/5 and positive 3. After drawing a sketch of this graph by hand, we realize that this does not hold if it's in the interval negative 2/5 and positive 3. So basically, x has to be less than or equal to negative 2/5 and greater than or equal to 3 to satisfy this inequality. And yeah, that's all we had to do. So third problem was quite different. I think whenever you have an inequality problem with a fraction, I generally think it's easier to just graph it out. Since we're in pre-calc, we have the skill set to graph out functions, and this shouldn't, and graphing this out actually, um, you know, gets rid of, having to do a lot of annoying casework. So whenever we're graphing a function, we want to first find end behavior. So, first let's see what happens as x becomes arbitrarily large. So when it goes to infinity, this expression is going to be negative 1, right? We just look at the coefficients of the x terms. That's going to be the ratio of these is negative 1. Same thing with as x goes to negative infinity, because this is going to be positive, but this is going to be negative. So the ratio of these would still be negative 1. So as x goes to positive infinity and as x goes to negative infinity, the horizontal asymptote of this expression is negative 1. At x equals 0, and generally you want to find, after you find end behavior, you want to find the zeros in the graph and put the x and the y intercepts. So the y-intercept is at 0, 2, which is positive. And the x-intercept is at x is equal to positive 2. We also have to know that this expression has a vertical asymptote at x equals to negative 1. So we also have to, check the behavior of this expression near its asymptote. So as we approach the asymptote of this graph from the left-hand side, which means, negative 1.1, negative 1.00001, negative 1.0000001, right? As x becomes very close to negative 1, this is going to blow up to negative infinity. And that's because this x plus 1 term is going to be, a value that's very close to 0, like immensely close to 0, but it's still going to be negative. Which is why this is going to blow up to negative infinity. And as we approach x negative 1 from the right, negative 0.9999, negative 0.99989, right? This is going to be super close to 0, but it's still going to be positive, right? The numerator is going to be positive in both cases, so we only care about the sign of the denominator. And as x approaches negative 1 from the right, this is going to blow up to positive infinity. So now we have, the behavior of this function, general behavior of this expression. And I think we can graph it out pretty easily. So, after graphing, we see that, this expression is less than or equal to 0 when x is in the intervals negative infinity, comma negative 1, which is open interval, and 2 comma infinity, the closed interval, like 2 is also counted. And that's our answer. Negative infinity, comma negative 1, and 2 comma infinity. All right, now let's move on to another topic that's quite important when you're dealing with, raw data. And this is usually used in a lot of scientific disciplines. It's used a lot in machine learning. So this is also a very important topic. And, what is regression? And it's basically, we're trying to use, we have raw data and we're trying to find a relationship in the form of a mathematical equation between those groups of data so that we can make more further, we can make a lot more predictions on what's going to happen when we change, values of that data. And I think one of the simplest applications of regression is a line of best fit, which we use a lot in science experiments. All right, here's an example problem. And solving any regression problem that asks you to make a prediction on a set of data is very simple, and it follows a really steady sequence and common sequence of steps. So our first step is to make a scatter plot. So, I highly encourage you to have your calculator out, a graphing calculator out. And depending on your calculator, I know what model you have. But you can use Excel for sure, or Google Drive. I think has a plugin that allows you to find linear regression. So you first make a scatter plot, and then you can either in this case we're using an exponential function to model the data. But in most cases, when you don't know what type of regression it is, you're gonna try exponential regression, logarithmic regression, logistical growth, everything, right? And you're just gonna pick the one with the highest R squared, which is basically how well the regression curve fits the data, and you're gonna use that form of regression. In this case, since it says exponential regression here, we're just going to find an exponential function to model the data. And we're going to graph the regression equation and the scatter plot on the same screen, and we're going to use this model to make a prediction. So, this is the process that we use for all types of regression. So I highly encourage you to, try to internalize all of this. All right, so first step one, make a scatter plot. So here's a screenshot of my calculator. So TI-84, but it does the job. So this is my scatter plot. Then you find an exponential function to model the data. And depending on the calculator, you can either use this. I'm not sure if your calculator has some other steps, so I highly encourage you check with your calculator's manual or find some YouTube video on how to do that. But the principle is the same. We're trying to find the coefficients of the general exponential function. All exponential functions are going to follow this y is equal to a times b to dx formula. So it's all a matter of finding the coefficients. And then we're going to find the r squared. Notice how this is so close to 1. Basically, what this means is that the line of best fit, essentially, it fits this almost perfectly. So, once you graph it, we can see from the r squared that this fits it very well. And then we use the model to make a prediction. So, we in our calculator, we solved for the coefficients, and now we're just gonna plug in the value into this general equation. After we find the coefficients, we essentially have our general equation. So we plug this into our general equation, and we can evaluate, our prediction. And this answer to the sample question is 26,013 bacteria. So There we go. So here's some practice problems. This topic is generally not very advanced, in my opinion, which is why I think you should be able to get through this with almost no effort. But if you're not able to, don't don't be too hard on yourself. Obviously, um, right. Before. Okay, so this is problem 1, problem 2, and problem 3. And before I talk about the solution to these problems, I highly encourage you, as I said before, to pause this video and try these for yourself. So once again, this is problem 1, problem 2, and problem 3. All right, memory. A group of students studied a photograph for 30 seconds. Beginning 1 day later, a test was given each day to test their memory of the photograph. The average score for each day is shown in the table. Use logarithmic regression to model the data. Then use your model to predict the average test score after 2 weeks. Once again, this is fairly straightforward. We already know what type of regression we're going to use. It's logarithmic, which means it's going to, follow the general formula y is equal to, some coefficient times log x base b, right? And we have to find the coefficient and, the base. So we're first gonna, okay, here's our answer, but here are the steps. So first, this is the plot of the scatter plot, right? We first plot a scatter plot. So I went into my graphing calculator, plotted all these values. Then I calculated the regression using ln RG and the correlation coefficient, which is r. We generally care about r squared. So the square of this is going to be, quite close to 1 as well. And, rounding each value, a natural logarithm is this. So we get this through using linear regression through our calculator. And this is our resulting function. As you can see, the r squared is very close to 1. And it makes sense, right? This graph is quite close to the data. It models it pretty well. And now we just, now we can just plug in values of x into our function. And since we want to predict the average score after 14 days, we just find the y value of this function at x is equal to 14. And once we plug in 14 to 73.1 minus 7.3 1 ln of 14, we get something that's roughly around 53.8%. All right, problem 2. Let me go back to problem 2. The number of television ads for a certain product affects the percentage of people who purchase the product as shown in the table. Use logistic regression to find a logistic growth function to model the data. Then use your model to predict the limit to the percentage of people who will purchase the product. All right, so the general formula for a logistic growth function is, let me try this out. All right, so f of x is equal to our carrying capacity. I'm just going to call that C over 1 plus a coefficient, so let's call that K, times e to the negative a t ax. This is in terms of x. I'm sorry if I didn't write that down well. Let me actually try writing that again. Actually. So f of x is equal to a over 1 plus e to the negative a t. There we go. This is our general formula for logistical growth. All right, so we want to find our logistical growth model. That's our logistical growth function. So we want to find the coefficients a and k, which shouldn't be too bad. So first thing first is to plot all this data, right? You want to plot it, scatter plot. So we're gonna plot it right over here, and let me get rid of this. Sorry, guys. Right. So I'm gonna plot it, and this is our scatter plot, and this is in the general shape of a logistical growth function. If you don't know what a logistical growth function looks like, it looks something like this. Right? 0 here. And this is our carrying capacity A. And the reason why A is our carrying capacity is if we take the limit of this function as t, or I should have written x, but as x goes to infinity, E is going to be 0. So it's just going to be A over 1 plus 0, which is A. So as time becomes larger and larger, or as x becomes arbitrarily large, the value of the function is going to approach A from below. All right. So we know it resembles the graph of a logistical growth function. All right. Cool. Now we're going to calculate logistical regression. And depending on your calculator, I don't know what model you use. I highly suggest look at your manual, look online or something. After we plot it, this is our coefficients. Okay, cool. All right. Oh, I think I forgot to also add that there has to be a coefficient over here. I'm sorry, guys. My bad. But, there's a coefficient e to the negative kt has a coefficient right here. All right, so it's going to solve all these coefficients, and then we get our general equation, and it's going to fit the data really well because the r squared is going to be very close to 1. Yeah, we just plug in our values, and the limit is 55.86 or 56%. The question was asking, as x becomes arbitrarily large, what will be the maximum value? And to do that, all we have to do is look at the coefficient, which is, a. And in this case, it's 55.86, which is approximately 56%. Problem 3. Let's move on to problem 3. Clear some of this. Alright, sorry for the delay. So, internet. Use the data in the table to determine a regression equation that relates the profit of a website at the time it has been in business. Then determine the approximate time it will take for the website to earn a profit of $100,000 in 1 year. Alright, now I think we first have to notice that the type of regression equation is not given. So we're going to have to try, everything that we've covered before. Linear regression, logistical regression, logarithmic regression, exponential regression, right? All 4 types of regression. All right. So, we still do the same thing though. We still have to follow the steps, and we're first gonna plot the data. And this looks like it's exponential, right? So we might have exponential might be the best option in this case. We're still gonna be trying every single equation though, and we're just gonna look at the corresponding correlation coefficients, basically our r squared or r value. And the regression equation with the coefficient closest to 1 after doing all these is the exponential regression. And that makes sense. I mean, look at this graph. It has to be exponential. So, after we get our coefficients from using exponential regression, we get 1,000 and 1.78. Now we can plug in our values, right? And, this is our corresponding regression curve. It fits it very well. Now we use the calc intersect to find, oh, wait. Sorry, we're solving for time t. Okay, we're just gonna find when this function we get after using linear regression reaches 100,000, which is not far off from plugging in. We're just gonna use and solve if you have a TI-89, or you can just graph it out and find the intersection where the two graphs intersect, and this is about at around 7.99. So this is when, or this is the amount of time it's going to take to reach $100,000. And that's it. Regression wasn't too bad. Yeah. Well, thank you for watching.